So we know 48.5 grams of iron oxide are reacting, and we know that there is a 1:1 molar ratio of iron oxide to aluminum oxide. So therefore, if we're using 48.5 grams of iron oxide, we must produce 48.5 grams of aluminum oxide, right? No! The stoichiometric ratios are molar ratios. They don't tell us anything about the number of grams that are going to get made, or even the number of grams of another reactant that are needed. The stoichiometric ratios, defined by the coefficients in the chemical equation, only describe molar ratios. But if we want to make a certain amount of product in the lab, we can't really measure out a number of moles. I doubt you're going to have a mole meter that's going to just be able to count out all the number of molecules in a sample. What you are going to have, though, is a balance, a scale that'll tell you the mass of a sample. So you can easily measure grams, but not moles. So what you're going to have to end up doing is converting between grams and moles a lot. We can only relate the amount of one reactant to the amount of product it'll make through the number of moles. So the first thing we have to do is to convert to moles. And I'm going to write out a game plan for our solution strategy. We're starting with grams of reactant. Let's write it as RCT. So once we have moles, we can easily use stoichiometric ratios to find either the moles of another reactant needed, or what we really want, the moles of products created, ideally. In real life, a reactant isn't going to produce all of the products it possibly could. There's going to be some that is lost or undergoes a different reaction. And we're going to be interested in figuring out exactly how much products we actually did make. So again, it's going to be very difficult to measure in moles how much product was made, but we could easily drop our sample on the scale and measure in grams. So we're often going to want to know how many grams of product we should make, which is what this question wants to know. So this plan here is a general strategy that you have to use for any stoichiometry problem, although you might have to adapt the strategy. If you want to find out how much of another reactant to use, for example, if we wanted to find out how much aluminum to use, we would still have to go from grams to moles of the first reactant to moles of the second reactant, and then grams of the second reactant. Since we already know the molar mass of all these compounds, it's not too hard to just go through these steps. And here I'm going to convert to moles of our reactant using the molar mass of Fe2O3. Which is 159.7 grams per mole. So if we were to stop and put these numbers in our calculator now, we would have moles of Fe2CO3. Now we just use the 1:1 molar ratio of Al2O3 to Fe2O3 to basically just show that there's the same number of moles of Al2O3 as Fe2O3. And by writing this in, we can very clearly show that we have canceled moles of iron oxide. So at this point here, we have moles of our product, aluminum oxide, because that's the unit we're left with. So we just need to do one more conversion using the molar mass of aluminum oxide, which is 102. So I've put in the molar mass, 102 grams of aluminum oxide, divided by 1 mole of aluminum oxide. And the moles of aluminum oxide cancel, and we are left with grams of aluminum oxide, which doesn't exactly show here. So we saw the strategy for stoichiometry problems. Grams of reactant to moles of reactant, which allows us to find moles of product. And then we can find grams of product. But what if we have a problem that asks us how much reactant we need to produce a certain amount of product? Well, then we can just do this whole thing backward. We start with however many grams of product we know we want to create, then work backwards to find the moles of the product, find the moles of reactant we would need, and then convert to the grams of reactant we would be able to measure out on a balance. And I've just written this out left to right, so it makes sense to our brains. If we know the grams of products we need, convert to moles of products, moles of reactants, and then the grams of reactants we start with. It's also relevant to point out that if the question asks for moles of reactant, you can just stop there. Done. Or if the question gives you the moles of products that you're going to make and asks you to figure out the grams of reactants, then you can just start at moles of product and go to grams of reactant. If we want to find out how much iron gets made, we do a very similar approach where we go from grams of reactant to moles of reactant to moles of iron product, and then to grams of iron product. So the first step is the same, to convert to moles, using the molar mass as a conversion factor. And that brings us here. And now, to convert from moles of reactant to moles of product, we need to use stoichiometric ratios. So we need to remember what the balanced equation was. The coefficients tell us that there's a 2:1 iron to iron oxide ratio. So we can use that ratio as a kind of conversion factor. There's 2 irons for every iron oxide. So that brings us here on our journey. So if we were to stop and do the math now, our answer would be in moles of iron. But we can go ahead and continue and convert to grams of iron using iron's atomic mass. And that should leave us with grams of iron as our unit.